What if everything you thought you knew about the universe was just the tip of the iceberg? Picture this, a vast, endless expanse of darkness, dotted with stars, galaxies, and mysteries that defy explanation. But what if I told you that some of these mysteries aren't just unanswered questions, they're downright unsettling? Welcome to a journey through 20 creepy theories about the universe, ideas that will make you question the very fabric of reality. From the possibility that we're living in a simulation to the chilling silence of alien civilizations, these theories don't just challenge our understanding of the cosmos, they shatter it. So buckle up, because by the end of this video, you might never look at the night sky the same way again. Stay with us as we dive into the eerie, the bizarre, and the mind-bending secrets of the universe. Now, turning to the first of these unsettling theories, let's explore the simulation hypothesis. Imagine for a moment that everything around you, the stars, the planets, even your own thoughts, might not be real. What if our entire universe is nothing more than a highly advanced simulation, created by a higher intelligence far beyond our comprehension? This idea, known as the simulation hypothesis, suggests that what we perceive as reality could be an intricate digital construct, much like a video game but on a cosmic scale. The roots of this theory trace back to philosopher Nick Bostrom, who argued that if a civilization could reach a level of technological sophistication capable of creating such simulations, it's statistically likely that we are living in one. Think about it. If future civilizations could run countless simulations of their ancestors, the odds of us being in the original, base reality are slim. This theory doesn't just raise questions about the nature of reality, it challenges our understanding of free will, existence, and even the meaning of life. If we're living in a simulation, are our choices truly our own, or are they pre-programmed? And if so, who or what is running the program? Over the years, this idea has gained traction not just in philosophical circles but also among scientists and tech leaders, sparking debates about the very fabric of our existence. It's a theory that doesn't just make you question the universe, it makes you question everything. Now, turning to the next unsettling theory, let's dive into the Boltzmann Brain Paradox. Imagine this, floating in the vast emptiness of space, a fully formed, self-aware brain suddenly comes into existence, complete with memories, thoughts, and a sense of identity, all created by random quantum fluctuations. This bizarre concept, known as the Boltzmann Brain Paradox, challenges our understanding of reality in ways that are both fascinating and deeply unsettling. The idea stems from the second law of thermodynamics, which states that entropy or disorder in the universe tends to increase over time. But in an infinite universe, given enough time, even the most improbable events could occur, including the spontaneous formation of a conscious brain. The paradox raises a chilling question. If such a brain could form randomly, how do we know that we're not just Boltzmann brains ourselves, existing for a fleeting moment with false memories of a past that never happened? This theory doesn't just question the nature of consciousness, it forces us to confront the possibility that our entire sense of reality could be an illusion. What if everything we perceive, from the stars above to the ground beneath our feet, is nothing more than a brief, random fluctuation in the void? The Boltzmann Brain Paradox leaves us grappling with the eerie uncertainty of our own existence, reminding us just how strange and mysterious the universe truly is. Now, turning to the next unsettling mystery, let's explore the Fermi Paradox and the Great Filter. Imagine looking up at the night sky, filled with billions of stars, and realizing that despite the overwhelming odds, we've never encountered any signs of intelligent alien life. This eerie silence is at the heart of the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everyone?" Given the vastness of the universe and the high probability of life-sustaining planets, it seems almost impossible that we're alone. Yet the silence is deafening. One chilling explanation for this cosmic quiet is the Great Filter theory. This idea suggests that there's some kind of barrier, a filter, that prevents civilizations from reaching a stage where they can communicate across the stars. The terrifying part, this filter could lie ahead of us. It might be something that causes advanced civilizations to self-destruct before they can achieve interstellar communication, whether through war, environmental collapse, or some other catastrophic event. If this is true, it raises a haunting question. Are we destined to face the same fate? The Great Filter forces us to confront the possibility that humanity's future might be far more fragile than we'd like to believe. It's a sobering reminder that our survival as a species is not guaranteed, and the silence of the universe might be a warning we can't afford to ignore. Now turning to another chilling possibility, let's delve into the dark forest hypothesis. This theory paints a stark and unsettling picture of the universe, suggesting that alien civilizations might be intentionally silent, not because they don't exist, but because they're hiding. The idea stems from game theory, which studies how rational beings make decisions in competitive or hostile environments. In this scenario, the universe is like a dark forest, where every civilization is a hunter, wary of revealing its presence. The reasoning is simple. Any advanced civilization you encounter could see you as a threat or a resource to exploit. To avoid annihilation, the safest strategy is to stay hidden and strike first if necessary. This grim outlook is deeply rooted in the fear of the unknown and the assumption that survival in the cosmos is a zero-sum game. Science fiction has explored this concept in works like Liu Cixin's The Three-Body Problem, where the dark forest hypothesis is central to the story. The theory forces us to confront a disturbing question. Could the silence of the universe be a sign that every civilization is too afraid to reach out? If true, it suggests that interstellar communication might not lead to friendship or discovery, but to conflict and destruction. The dark forest hypothesis offers a haunting perspective on our place in the cosmos, reminding us that the universe might be far more dangerous and far lonelier than we ever imagined. Now turning to another mind-bending possibility, let's explore the Big Crunch and the Cyclic Universe theory. This idea suggests that the universe, which began with the Big Bang, might one day collapse back into a singularity, a single point of infinite density. Imagine the cosmos as a cosmic rubber band, stretching out during its expansion but eventually snapping back together. This collapse would trigger another Big Bang, starting the cycle all over again. The Big Crunch theory is rooted in the idea that gravity, the force pulling everything together, could eventually overcome the expansion of the universe. If there's enough matter and energy, gravity might slow down and reverse the expansion, leading to a dramatic collapse. However, this theory faces challenges. Observations of distant galaxies suggest that the universe's expansion is accelerating, not slowing down, due to the mysterious force known as dark energy. This has led many scientists to favor the Big Freeze theory, where the universe continues to expand forever, growing colder and darker until all energy is spread too thin to sustain life. But the Big Crunch offers a fascinating alternative, a universe that breathes in and out, expanding and contracting in an endless cycle. This cyclical nature of existence raises profound questions about time, eternity, and the very fabric of reality. Could the universe be caught in an infinite loop of birth, death, and rebirth? If so, it suggests that everything we know, every star, every planet, every life, might have existed countless times before and will exist again. The Big Crunch theory invites us to ponder the possibility that the universe is not just a one-time event, but an eternal dance of creation and destruction. Now turning to another astonishing idea, let's dive into the multiverse theory. This concept suggests that our universe might not be the only one. Instead, there could be an infinite number of parallel universes, each with its own set of physical laws and outcomes. Imagine a cosmic library where every book tells a different story of existence, with some universes resembling ours and others so bizarre they defy imagination. The roots of this theory lie in quantum mechanics and string theory, which propose that at the most fundamental level, reality is far stranger than we can perceive. In quantum mechanics, particles exist in multiple states simultaneously until observed, a phenomenon known as superposition. Some interpretations suggest that every possible outcome of a quantum event actually happens but in separate universes. This means that every decision you make, whether to turn left or right, to speak or stay silent, could spawn a new universe where the alternative choice plays out. The implications are staggering. It challenges our understanding of uniqueness and destiny, suggesting that there might be countless versions of you, living countless lives in countless realities. The multiverse theory also raises eerie questions about the nature of existence. If every possible universe exists, does that mean there's a universe where the laws of physics allow for magic, or where time flows backward? And if so, what does that say about our own reality? Are we just one thread in an infinite cosmic tapestry? This theory doesn't just expand our view of the cosmos, it shatters it, forcing us to confront the possibility that our universe is just one tiny piece of a much larger, more mysterious puzzle. As we ponder the multiverse theory, we're left to wonder, in the grand scheme of existence, how unique are we really? And if every choice creates a new reality, what does that mean for the concept of free will? The answers remain elusive, but the questions themselves are enough to keep us staring at the stars, searching for clues in the vast, unknowable expanse of the multiverse. Now turning to a chilling yet inevitable possibility, let's explore the heat death of the universe. This theory paints a picture of the cosmos not with a dramatic explosion or collapse, but with a slow, silent fade into darkness. According to this idea, the universe will eventually reach a state of maximum entropy, where all energy is evenly distributed, and no usable energy remains to sustain life, motion, or even the stars themselves. Imagine a cosmic engine running out of fuel, gradually grinding to a halt. The scientific basis for this theory lies in the second law of thermodynamics, which states that entropy, or disorder, in a closed system always increases over time. In simpler terms, energy naturally spreads out and becomes less concentrated, making it harder to harness for work or activity. Over billions of years, stars will burn out, galaxies will drift apart, and even black holes will evaporate through a process known as Hawking radiation. What will be left is a cold, dark, and lifeless expanse where nothing happens, a universe in a state of perfect equilibrium, but also perfect stillness. The implications of this theory are profound. It suggests that all the complexity, beauty, and life we see around us is temporary, destined to fade into oblivion as the universe marches toward its ultimate fate. It raises unsettling questions about the purpose of existence and the legacy of humanity. If the universe is doomed to end in heat death, does anything we do truly matter in the grand scheme of things? And yet, even in this bleak scenario, there's a strange kind of beauty. The heat death of the universe reminds us of the fleeting nature of existence and the preciousness of the time we have. It challenges us to find meaning not in the infinite but in the here and now. As we contemplate this theory, we're left to wonder, in a universe destined for stillness, what will we leave behind? And how can we make the most of the energy we have while it lasts? The answers may lie not in the stars but within ourselves. Now turning to one of the most perplexing mysteries in modern physics, let's delve into the black hole information paradox. This theory revolves around a fundamental question: what happens to information that falls into a black hole? According to our current understanding of physics, information, whether it's the position of a particle or the details of a star, can never be completely destroyed. Yet, black holes seem to defy this principle. When matter is pulled into a black hole, it's crushed into an infinitely dense point called a singularity, leaving no trace of the original information. This creates a paradox that has puzzled scientists for decades. The debate intensified when Stephen Hawking proposed that black holes aren't entirely black. Instead, they emit a faint radiation, now known as Hawking radiation, which causes them to slowly lose mass and eventually evaporate. But here's the catch: if a black hole evaporates completely, what happens to all the information it swallowed? Does it vanish forever, violating the laws of quantum mechanics, or is it somehow preserved in the radiation? This question has sparked heated discussions among physicists, with some suggesting that information might be encoded in the Hawking radiation, while others argue it could be stored in a hidden layer at the black hole's event horizon. The implications of this paradox are staggering. If information is truly lost, it would mean rewriting some of the most fundamental laws of physics, including the principle of conservation of information. On the other hand, if information is preserved, it could revolutionize our understanding of space, time, and the very fabric of reality. The black hole information paradox isn't just a theoretical puzzle, it's a gateway to uncovering deeper truths about the universe. As we grapple with this mystery, we're reminded that even the most enigmatic phenomena hold the potential to reshape our understanding of existence. What secrets might black holes still be hiding? And how will solving this paradox change the way we see the cosmos? The answers could lie at the very edge of our knowledge, waiting to be discovered. Now turning to a theory that could completely redefine our perception of reality, let's explore the holographic principle. This mind-bending idea suggests that the universe we experience, with its 3 dimensions of space and 1 of time, might actually be a 2-dimensional hologram projected onto a vast cosmological horizon. Imagine the entire cosmos as a kind of cosmic movie screen, where everything we see, touch, and feel is just a projection of information encoded on a flat surface. It sounds like science fiction, but this theory has deep roots in the cutting-edge realms of string theory and black hole physics. The holographic principle first emerged from the study of black holes, particularly the work of physicist Gerard T. Hooft and later Leonard Susskind. They proposed that all the information about matter and energy falling into a black hole isn't lost but is instead encoded on its event horizon, the boundary beyond which nothing can escape. This idea led to the startling realization that the universe itself might operate in a similar way, with all the information about our 3-dimensional reality stored on a 2-dimensional surface at its edges. But how could this be possible? According to string theory, the fundamental building blocks of reality are not particles but tiny, vibrating strings of energy. These strings exist in higher dimensional spaces, and the holographic principle suggests that the interactions of these strings in higher dimensions could be projected as the 3-dimensional universe we perceive. In other words, our reality might be a kind of cosmic illusion, a hologram created by the interplay of information on a 2-dimensional plane. The implications of this theory are nothing short of revolutionary. If the holographic principle is true, it could mean that space and time are not fundamental aspects of the universe but emergent properties arising from deeper, more fundamental layers of reality. This would challenge our most basic assumptions about existence and open up entirely new ways of understanding the cosmos. It could also provide a unified framework for reconciling quantum mechanics and general relativity, 2 pillars of modern physics that have so far resisted integration. As we ponder the holographic principle, we're left with profound questions about the nature of reality itself. Is the universe truly a hologram? And if so, what does that mean for our understanding of space, time, and our place within the cosmos? The answers to these questions could reshape not only physics but also our very perception of existence. What other secrets might the universe be hiding, and how will this theory guide us toward uncovering them? The journey to understanding the holographic nature of reality is just beginning, and the possibilities are as vast as the cosmos itself. Now turning to a theory that could spell the end of everything we know, let's explore the unsettling concept of the false vacuum collapse. This idea suggests that our universe might not be as stable as it seems. Instead, it could exist in a precarious state known as a false vacuum, a temporary, high-energy condition that could collapse into a lower energy state at any moment. Think of it like a ball perched on the edge of a hill. It seems stable for now, but the slightest nudge could send it tumbling down, triggering a catastrophic chain reaction. If such a collapse were to occur, the consequences would be unimaginable. The laws of physics as we know them would fundamentally change. Atoms, the building blocks of matter, might no longer hold together. Stars, planets, and even life itself could cease to exist in an instant. The universe as we know it would be rewritten, and there would be no warning, no way to prepare. One moment, everything would seem normal, and the next, reality itself would unravel. What makes this theory even more unsettling is the possibility that it could happen at any time. The collapse could be triggered by a random quantum fluctuation, a cosmic event, or even something as small as a particle collision in a laboratory. The universe's transition to a lower energy state would spread at the speed of light, meaning we wouldn't see it coming until it was too late. It's a chilling reminder of how fragile our existence might truly be. But why would the universe be in such a precarious state? According to quantum field theory, the vacuum of space isn't empty but filled with energy fields. These fields can exist in different states, much like water can exist as ice, liquid, or steam. Our universe might currently be in a high-energy state, like superheated water, waiting to transition to a more stable, lower-energy state. The problem is, once that transition begins, there's no going back. The false vacuum collapse theory forces us to confront the fragility of reality and the possibility that the universe as we know it could end in an instant. It's a sobering thought, but it also highlights the incredible complexity and mystery of the cosmos. As we continue to explore the nature of the universe, theories like this remind us that there's still so much we don't understand, and that the answers we seek might be as unpredictable as the universe itself. What other hidden dangers might lurk in the fabric of reality, and how will we uncover them? The journey to understanding the universe's deepest secrets is far from over. Now turning to a theory that blurs the line between life, death, and the very nature of existence, let's delve into the Quantum Immortality Theory. This mind-bending idea suggests that consciousness might never truly end, even if death occurs in one universe. According to this theory, rooted in the many worlds interpretation of quantum mechanics, every possible outcome of an event actually happens, but in separate, branching universes. So, if you were to face a life-threatening situation, there's always a universe where you survive, and your consciousness continues in that reality. Imagine this: you're in a situation where the odds of survival seem impossibly low. In one universe, you might not make it, but in another, you miraculously do. According to quantum immortality, your consciousness would always follow the path where you continue to exist, no matter how unlikely it seems. It's as if you're perpetually shifting into the universe where you're still alive, while other versions of you cease to exist in parallel realities. This theory raises profound philosophical and existential questions. If consciousness can persist indefinitely across alternate universes, does that mean we're immortal in some sense? And if so, what does that say about the nature of death? Is it merely a transition from one reality to another, or does it hold a deeper meaning? These questions challenge our understanding of life, identity, and the very fabric of reality. The quantum immortality theory also forces us to confront the eerie possibility that we might never truly experience death from our own perspective. While others might observe our passing in one universe, our consciousness would always shift to a reality where we're still alive. It's a concept that feels both comforting and unsettling. Comforting because it suggests a form of immortality, but unsettling because it implies that death, as we understand it, might be an illusion. But how does this theory hold up scientifically? The many worlds interpretation which underpins quantum immortality is one of several interpretations of quantum mechanics. While it's a legitimate framework, it's not without its critics. Some argue that it's untestable, as we can't observe or interact with these alternate universes. Others question whether consciousness truly has the ability to choose which reality to inhabit. Despite these debates, the theory remains a fascinating exploration of the intersection between quantum physics and the mysteries of existence. As we ponder the implications of quantum immortality, we're left with more questions than answers. What does it mean to be alive if death is just a shift in perspective? And if we're immortal in some sense, how does that shape our understanding of purpose and meaning? These are the kinds of questions that keep us staring at the stars, wondering just how strange and infinite the universe and our place within it might truly be. Now turning to a concept that flips the script on one of the universe's most mysterious phenomena, let's explore the white hole theory. Imagine a black hole, but in reverse. Instead of pulling everything in, a white hole would violently expel matter and energy into the cosmos. This theoretical counterpart to black holes has fascinated scientists and science fiction enthusiasts alike, offering a tantalizing glimpse into the strange symmetries of the universe. White holes are predicted by the same equations that describe black holes, specifically Einstein's theory of general relativity. While black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape, white holes are thought to be regions where matter and energy are ejected outward, never to return. In essence, a white hole would be like a cosmic fountain, spewing out material at incredible speeds, while a black hole is more like a cosmic drain. But here's the catch: white holes are purely theoretical. No one has ever observed one, and their existence remains a subject of debate. Some scientists argue that white holes could be the other end of a black hole, connected by a theoretical tunnel known as a wormhole. In this scenario, anything that falls into a black hole in one part of the universe could be ejected from a white hole in another. It's a mind-bending idea that suggests the universe might be far more interconnected than we realize. Others propose that white holes could be the remnants of black holes that have reached the end of their life cycle. According to this idea, when a black hole evaporates completely through a process known as Hawking radiation, it might leave behind a white hole as its final act. This would mean that white holes are not just theoretical curiosities, but could be a natural part of the cosmic life cycle. The implications of white holes are as fascinating as they are speculative. If they exist, they could help explain some of the universe's most puzzling phenomena, such as the origins of gamma-ray bursts or the mysterious dark energy driving the universe's accelerated expansion. They might even offer a way to reconcile the laws of physics, bridging the gap between quantum mechanics and general relativity. Yet, for all their potential, white holes remain shrouded in mystery. Their existence challenges our understanding of spacetime, gravity, and the very nature of the universe. Are they real, or are they just mathematical curiosities? Could they be the key to unlocking some of the cosmos's deepest secrets, or are they destined to remain a tantalizing what-if in the annals of astrophysics? As we ponder the possibilities, one thing is clear: the universe is full of surprises, and white holes are just one more reminder of how much we have yet to discover. Whether they exist or not, they inspire us to keep exploring, to keep questioning, and to keep marveling at the infinite mysteries of the cosmos. Now turning to a theory that reimagines the very birth and death of the cosmos, let's explore the Big Bounce theory. This idea suggests that the universe doesn't have a single beginning or end, but instead undergoes endless cycles of expansion and contraction. Imagine the universe as a cosmic accordion, breathing in and out over unimaginable stretches of time. Each breath begins with a big bang, expands outward, and eventually collapses back into a singularity, only to explode again in a new big bang. It's a cyclical view of existence that challenges the traditional idea of a one-time Big Bang as the origin of everything. The Big Bounce theory is rooted in the mathematics of general relativity and quantum mechanics. It proposes that when the universe reaches its maximum size, the force of gravity becomes so strong that it halts expansion and pulls everything back together. This collapse doesn't end in destruction, but instead creates the conditions for a new Big Bang, starting the cycle all over again. In this way, the universe could be eternal, with no true beginning or end, just an endless dance of creation and destruction. But what evidence supports this idea? Some scientists point to the cosmic microwave background radiation, the faint afterglow of the Big Bang, as a potential clue. Tiny fluctuations in this radiation might carry imprints of previous cycles, like echoes of a universe that existed before ours. Others argue that the Big Bounce could help explain the mysterious uniformity of the universe on large scales, as each cycle might reset the cosmos, smoothing out irregularities over time. However, the Big Bounce theory is not without its critics. One major challenge is the question of what happens during the bounce itself. The laws of physics as we know them break down at the point of singularity, making it difficult to predict how the universe could transition from collapse to expansion. Some physicists argue that the Big Bounce might require new physics, such as a quantum theory of gravity, to fully explain the process. Despite these uncertainties, the Big Bounce offers a compelling alternative to the traditional Big Bang model. It suggests that our universe might be just one chapter in an infinite cosmic story, with countless cycles of birth, death, and rebirth stretching into the past and future. This idea not only reshapes our understanding of the universe's origins, but also raises profound questions about the nature of time, existence, and the ultimate fate of everything we know. As we consider the possibilities, the Big Bounce theory reminds us that the universe is far stranger and more dynamic than we often imagine. Whether it's a single, explosive beginning or an endless cycle of renewal, the cosmos continues to challenge our understanding and inspire our curiosity. And with that, we move forward to another mind-bending theory that pushes the boundaries of what we think we know. Now turning to a theory that paints a chilling picture of the universe's ultimate fate, let's explore the phantom energy theory. This idea revolves around a hypothetical form of dark energy known as phantom energy, which could accelerate the expansion of the universe to such an extreme degree that it tears itself apart. Imagine a force so powerful that it doesn't just push galaxies apart but rips apart the very fabric of space and time. This scenario, known as the Big Rip, is one of the most unsettling possibilities for how the cosmos might end. Phantom energy is a speculative concept that takes the idea of dark energy, the mysterious force driving the universe's accelerated expansion, to its most extreme conclusion. Unlike ordinary dark energy, which causes a steady expansion, phantom energy would grow stronger over time. As the universe expands, phantom energy would increase in density, creating a feedback loop that accelerates expansion faster and faster. Eventually, this runaway effect could become so intense that it overcomes all other forces in the universe, including gravity, electromagnetism, and even the nuclear forces holding atoms together. The implications of this theory are as dramatic as they are terrifying. In the final moments of a Big Rip scenario, the universe would unravel in stages. First, galaxies would be torn apart as the space between stars expands faster than gravity can hold them together. Next, stars and planets would disintegrate as the forces binding them are overwhelmed. Finally, even atoms and subatomic particles would be ripped apart, leaving behind a universe devoid of structure, energy, or life. It's a cosmic apocalypse unlike anything we've ever imagined. But what evidence supports the existence of phantom energy? So far, it remains purely theoretical, with no direct observations to confirm its existence. However, some scientists point to the accelerating expansion of the universe as a potential clue. If dark energy behaves in a way that aligns with phantom energy's predictions, it could hint at the possibility of a big rip in the distant future. Others argue that phantom energy might help explain certain anomalies in the cosmic microwave background radiation, though this remains a topic of debate. The phantom energy theory raises profound questions about the nature of the universe and our place within it. If the Big Rip is a real possibility, it challenges our understanding of time, space, and the fundamental forces that govern existence. It also forces us to confront the eerie reality that the universe might not end with a whimper, as in the Big Freeze, or a collapse, as in the Big Crunch, but with a violent, all-encompassing tear. As we ponder this unsettling theory, it's worth remembering that the universe is full of mysteries we have yet to unravel. Whether phantom energy exists or not, the idea of a big rip reminds us of the fragility of the cosmos and the incredible forces that shape its destiny. And with that, we move forward to another theory that delves into the strange and mysterious nature of time itself. Now turning to a theory that bends the very fabric of time, let's explore the time loop theory. This idea suggests that the universe might be trapped in an endless cycle, repeating the same events over and over again. Imagine living the same moment, the same day, or even the same lifetime endlessly with no escape. It's a concept that challenges our understanding of time, free will, and the very nature of existence. The time loop theory finds its roots in both physics and philosophy. In physics, it draws inspiration from the concept of closed time-like curves, which are solutions to Einstein's equations of general relativity. These curves suggest that time could loop back on itself, creating a scenario where events repeat in an infinite cycle. Philosophically, the idea echoes ancient beliefs in eternal recurrence, where the universe is thought to undergo endless cycles of creation and destruction. One of the most unsettling aspects of this theory is its implications for free will. If the universe is stuck in a time loop, does that mean our choices are predetermined? Are we merely actors in a cosmic play, destined to repeat the same actions over and over? These questions strike at the heart of what it means to be human, challenging our sense of autonomy and purpose. The time loop theory also raises profound questions about destiny. If events are destined to repeat, does that mean the future is already written? Or is there a possibility for change within the loop, a way to break free from the cycle? These are questions that have fascinated thinkers for centuries, from ancient philosophers to modern scientists. While the time loop theory remains speculative, it offers a fascinating lens through which to view the universe. It challenges us to rethink our understanding of time, reality, and our place within the cosmos. And as we ponder these questions, we're reminded of the endless mysteries that the universe holds, waiting to be unraveled. With that, we move forward to another theory that delves into the strange and mysterious nature of the cosmos, where new challenges and revelations await. Now turning to a theory that takes us beyond the boundaries of our own world, let's explore the alien megastructure hypothesis. This idea centers around Tabby's star, a distant star located about 1,400 light-years away from Earth. What makes this star so intriguing is its unusual dimming pattern, which has baffled scientists and sparked one of the most fascinating theories in modern astronomy. Tabby's star, officially known as KIC 8462852, was first observed by the Kepler Space Telescope. Unlike most stars, which dim in predictable ways due to planets passing in front of them, Tabby's star exhibits irregular and dramatic dips in brightness. These dips can last for days or even weeks, and they don't follow any clear pattern. This strange behavior has led some scientists to propose an extraordinary explanation. The dimming could be caused by an alien megastructure. The idea is that an advanced extraterrestrial civilization might have built a massive structure, such as a Dyson sphere, around the star to harness its energy. A Dyson sphere is a hypothetical megastructure that completely or partially encloses a star, capturing its energy output for use by the civilization that built it. If such a structure exists around Tabby's star, it could explain the irregular dimming as the megastructure passes in front of the star from our perspective. While this theory is speculative, it has captured the imagination of scientists and the public alike. The search for extraterrestrial intelligence, or SETI, has long been a quest to answer the question of whether we are alone in the universe. The possibility that Tabby's star could be home to an alien megastructure adds a thrilling dimension to this search. It raises the eerie possibility that we might not be alone, and that somewhere out there, a civilization far more advanced than our own could be thriving. Of course, there are other, more conventional explanations for Tabby's star's behavior. Some scientists suggest that the dimming could be caused by a swarm of comets, dust clouds, or other natural phenomena. However, the alien megastructure hypothesis remains one of the most compelling and thought-provoking explanations. It challenges us to consider the vast possibilities of the cosmos and the potential for life beyond our own planet. As we continue to study Tabby's star and other mysterious objects in the universe, we are reminded of the endless questions that remain unanswered. The alien megastructure hypothesis invites us to dream big and to keep searching for the truth, no matter how strange or unsettling it may be. And with that, we move forward to another theory that delves deeper into the mysteries of the cosmos, where new discoveries and challenges await. Now turning to one of the most profound mysteries in modern astrophysics, let's explore the enigma of dark matter. This invisible substance makes up roughly 85% of the universe's total mass, yet it remains completely undetectable by conventional means. Despite its elusive nature, dark matter's gravitational effects are undeniable, shaping the very structure of the cosmos as we know it. The story of dark matter begins with observations that simply didn't add up. In the 1930s, astronomer Fritz Zwicky noticed that galaxies within galaxy clusters were moving far faster than they should have been, based on the visible matter alone. This discrepancy suggested the presence of something unseen, something massive enough to exert a gravitational pull but invisible to our telescopes. Decades later, Vera Rubin's groundbreaking work on galaxy rotation curves confirmed this strange phenomenon, solidifying the case for dark matter. So, what exactly is dark matter? The truth is, we don't know. It doesn't emit, absorb, or reflect light, making it impossible to observe directly. It doesn't interact with electromagnetic forces, which means it passes through ordinary matter as if it weren't even there. Yet, its gravitational influence is everywhere, from the way galaxies rotate to the way light bends around massive objects in a phenomenon known as gravitational lensing. Scientists have proposed numerous theories to explain dark matter's nature. Some believe it could be composed of weakly interacting massive particles, or WIMP, hypothetical particles that rarely interact with normal matter. Others suggest it might be made up of actions, another type of theoretical particle. There's even the possibility that dark matter isn't made of particles at all, but is instead a manifestation of modified gravity, a tweak to our understanding of how gravity works on cosmic scales. Despite decades of research, dark matter remains one of the greatest unsolved puzzles in science. Experiments like the Large Hadron Collider and observatories like the Dark Energy Survey continue to search for clues, but so far, dark matter has evaded detection. This raises an unsettling question. What if we never fully understand it? What if dark matter is simply beyond the reach of our current technology and understanding? The mystery of dark matter challenges us to rethink our assumptions about the universe. It reminds us that there is still so much we don't know, and that the cosmos is far stranger and more complex than we can imagine. As we continue to search for answers, we are left to wonder, what other secrets might the universe be hiding? And with that, we move forward to another theory that pushes the boundaries of our understanding even further, where new mysteries and revelations await. Now turning to another cosmic mystery, let's delve into the strange and unsettling anomalies found in the cosmic microwave background radiation, or CMB. This faint glow, often called the afterglow of the Big Bang, is the oldest light in the universe, dating back to just 380,000 years after the universe began. It's a snapshot of the infant cosmos, and yet within this ancient light, scientists have discovered peculiar patterns that defy explanation. The cosmic microwave background is remarkably uniform, but not perfectly so. Tiny fluctuations in temperature reveal the seeds of cosmic structure, the beginnings of galaxies and galaxy clusters. However, some of these fluctuations are far stranger than expected. One of the most puzzling anomalies is the so-called axis of evil, a mysterious alignment of temperature patterns that seems to suggest a preferred direction in the universe. This challenges the fundamental principle of cosmology known as the cosmological principle, which states that the universe should look the same in all directions. Another anomaly is the cold spot, a region of the CMB that is significantly colder than its surroundings. Some theories suggest this could be evidence of a collision with another universe in a multiverse scenario, while others propose it might be a vast cosmic void. Either way, the cold spot raises questions about the nature of our universe and whether it exists in isolation or as part of a larger, more complex reality. These anomalies aren't just quirks in the data, they could have profound implications for our understanding of the early universe. If the axis of evil and the cold spot are real, they might hint at physics beyond our current models, such as exotic forms of energy or even the existence of other universes. The idea of a multiverse, where our universe is just one of countless others, becomes even more intriguing when we consider these cosmic oddities. Yet, despite decades of study, the true nature of these anomalies remains elusive. Are they simply statistical flukes, or do they point to something far more profound? The eerie possibility that they could be evidence of a multiverse or other unknown phenomena challenges us to rethink our place in the cosmos. As we continue to study the CMB, we are left to wonder, what other secrets might this ancient light hold? And with that, we move forward to another theory that pushes the boundaries of our understanding even further, where new mysteries and revelations await. Now turning to another mind-bending mystery, let's explore the strange and fascinating phenomenon of quantum entanglement. This is the idea that two particles can become so deeply connected that the state of one instantly influences the state of the other, no matter how far apart they are in the universe. It's as if they share an invisible bond that defies the limits of space and time, and it challenges everything we thought we knew about reality. Imagine two particles, let's call them particle A and particle B, created together in a single event. According to quantum mechanics, these particles can become entangled, meaning their properties like spin or polarization are linked. If you measure the spin of particle A and find it spinning upward, particle B will instantly be spinning downward, even if it's on the other side of the galaxy. This connection happens faster than the speed of light, which seems to break one of the fundamental rules of physics. Nothing can travel faster than light. Albert Einstein famously called this spooky action at a distance, and for good reason. It's a concept that feels more like science fiction than science. But experiments have repeatedly confirmed that quantum entanglement is real. Scientists have sent entangled particles hundreds of kilometers apart and observed this instantaneous connection, proving that the universe operates in ways we're only beginning to understand. So, what does this mean for our understanding of reality? For one, it suggests that space and time might not be as fundamental as we once thought. If particles can communicate instantaneously across vast distances, it implies that the universe might be fundamentally interconnected in ways we can't yet fully grasp. Some physicists even speculate that entanglement could be a clue to a deeper, hidden layer of reality, a cosmic web that ties everything together. But the eerie implications don't stop there. Quantum entanglement also raises questions about the nature of free will and determinism. If the state of one particle is instantly determined by the state of another, does that mean the universe is preordained, or is there still room for randomness and choice? These are questions that blur the line between physics and philosophy, leaving us to wonder just how much control we really have over our own lives. As we continue to unravel the mysteries of quantum entanglement, one thing is clear: the universe is far stranger and more interconnected than we ever imagined. And with that, we move forward to our final theory, where the mysteries of the cosmos take us to the very edge of existence itself. Now, turning to our final and perhaps most mind-bending theory, let's explore the idea that our entire universe might exist inside a black hole. This theory suggests that the cosmos we know, the stars, galaxies, and even the fabric of space and time, could all be contained within the boundaries of a massive black hole. It's a concept that flips our understanding of reality on its head and raises profound questions about the origins and structure of existence. The idea stems from the similarities between the Big Bang and the formation of black holes. When we look at the equations describing the birth of the universe and the collapse of matter into a black hole, they appear strikingly similar. Both involve a singularity, a point of infinite density where the laws of physics as we know them break down. Some scientists propose that the Big Bang itself could have been the result of a black hole forming in a higher dimensional universe, with our universe emerging from its interior. But how could this work? Imagine a black hole in a larger parent universe. As matter falls into the black hole, it doesn't simply vanish. Instead, it could be compressed and stretched into a new region of space and time, creating an entirely new universe within the black hole. In this scenario, our universe would be one of countless others, each nested inside its own black hole like a cosmic Russian doll. This theory also offers a potential explanation for dark energy, the mysterious force driving the accelerated expansion of our universe. Some models suggest that the energy released by the black hole's formation could manifest as dark energy, pushing the universe outward and shaping its evolution over billions of years. The implications of this theory are staggering. If true, it would mean that every black hole in our universe could be the seed of a new cosmos, each with its own unique laws of physics and dimensions. It also raises the eerie possibility that our universe is just one layer in an infinite hierarchy of realities, each contained within another. As we ponder this theory, we're left with a profound question. If our universe is inside a black hole, what lies beyond its event horizon? Could there be other universes, other realities waiting to be discovered? The idea challenges not only our understanding of the cosmos, but also our place within it, leaving us to wonder just how deep the mysteries of existence truly go. Now, turning to the conclusion of our journey through these 20 eerie theories about the universe, let's take a moment to reflect on the mind-bending ideas we've explored. From the unsettling possibility that we might be living in a simulation to the haunting silence of the Fermi Paradox, each theory challenges our understanding of reality in profound ways. We've delved into the mysteries of black holes, the enigma of dark matter, and the chilling implications of the Great Filter. We've questioned whether our universe is a hologram, a time loop, or even a cosmic Russian doll nested within a black hole. These theories don't just push the boundaries of science, they force us to confront the very nature of existence itself. As we wrap up, one thing is clear: the universe is far stranger and more mysterious than we could ever imagine. Each theory we've discussed raises more questions than answers, leaving us to wonder just how much we truly understand about the cosmos. Are we alone in the universe, or is something or someone out there watching in silence? Could our reality be just one layer of an infinite multiverse, or are we living in a simulation created by an advanced civilization? The possibilities are as endless as the universe itself, So, what do you think? Which of these theories resonates with you the most, and which one keeps you up at night? Let us know in the comments below. We'd love to hear your thoughts and theories. And if you enjoyed this deep dive into the mysteries of the cosmos, don't forget to hit that like button, subscribe to the channel, and ring the notification bell so you never miss out on more mind-bending content. The universe is full of secrets waiting to be uncovered, and we're just getting started. Until next time, keep looking up and keep questioning everything.